So since the last video, I refactored our library quite a bit so that now, regardless of the dimension of whatever tensors we're working with, they always store their data in contiguous memory. So in this video, I'm going to explain exactly why it is that we did that and how that leads to performance boosts before we even get into multi-threading operations. So if we were to implement two-dimensional tensors in Rust in just the most straightforward way, we might do something like this, where our tensor object stores a vector where the first element of that vector points to a vector out on the heap that stores the data for the first row. And then the second element would point out to another vector that stores the second row, and so on and so forth. This is a really simple, really straightforward implementation for two-dimensional tensors, but it does create some problems, namely that it's a lot of jumping around in memory, right? If we want to read from the first row, we have to find it out on the heap. If we want to read from the second row, we have to find that out on the heap. If we want to read from the second column, then we have to access the vector from the first row. Then we have to jump to the vector for the second row, and then so on and so forth. So this creates a lot of movement in memory, which can be very expensive, especially for very large tensors. So a slightly different construction that we could use for this is just to store all the tensor data inside of a single block of contiguous memory. And this is really nice because we know exactly how to interact with this data structure based only on the dimensions of the tensor. So for instance, if we want to access the first row, we know that there are 4 columns in this tensor. So we start at the first element in the chunk of memory, and we just get the first 4 elements from our vector in Rust, right? If we want to get the first column, we know that we start at the first element of our vector, and then we then have a stride of 4. So if we move 4 elements to the right, we're now at the first element of the second row, or the second element of the first column. And if we take another stride of 4 to the right, now we're at the third element of the first column. So the first dimension of your tensor tells you basically how many strides you can take along this vector, and the second dimension tells you the length of that stride. So now we can switch up the tensor representation and notice that this is a 4x3, right? But we can still just use the same 12 blocks of memory. And now our stride is 3, and we can do this 4 times. So if we want to get the first column, start at the first element, 3 steps to the right gets you the second element of the first column, and so on and so forth. You can even do the same thing for 3-dimensional tensors. So, do this one, I guess, as an exercise in your head, but the idea is it doesn't really matter the representation of the tensor. All we care about is how many elements we need to store in memory, and then we know how to operate on that chunk based on the dimensions of the tensor itself. What this means is that we can effectively reshape a tensor by just changing its dimension. We don't have to affect the underlying memory, and that takes tensor reshape operations from like potentially O of n to O of 1, which is a massive performance boost. So the benefits, right, of changing our construction for tensors: we have fewer heap accesses, we can reshape in basically constant time. Another benefit here is that tensor ops, the implementations are the same for any dimensional vector, and I can show examples of that in the source code here at the end. For cons, the biggest drawback here is that you have to have enough memory to allocate contiguously in order to fit your tensor. So for instance, if we were trying to store a 400 billion parameter language model in memory, we would need to find a chunk of memory that has 400 billion elements in it that are adjacent to one another. Most systems, you're not going to find that. So that's a really big con, but we're not going to be operating on tensors of that size, so it doesn't really matter that much to us. If we were to do it, though, it could slow down your ops, which isn't great. PyTorch will break up very large structures into non-contiguous memory, but for the most part, this is kind of what you're working with, whether you're looking at torch tensors or you're looking at NumPy arrays. So in our source code here, you can see that now our constructor for our tensor, we just consume basically the dimensions for the tensor as well as the elements as a single contiguous chunk of memory. In this case, it's a slice if you're going to pass it directly. But the idea is all we have to do is just make sure that the length of the elements we're consuming is equal to the product of the dimensions. And as long as we meet that criteria, we know that we can represent this n-dimensional tensor given the amount of memory that we're allocating to store the elements. When we go ahead and we reshape, we just have to check that condition again. For the new dimensions that we're consuming, does the product of those dimensions equal the number of elements inside of the array? If that's true, then we know that we can reshape the tensor, and all we have to do is update the dimensions. So in order to print these tensors out to the console now, what we're doing is we're taking each row of the tensor, we're collecting all of the elements into a single comma delimited list, and then we just print that out to the console. As a simple exercise, let's start with a pretty straightforward 2x3 tensor. We'll print that out, and then we'll reshape it to a 3x2. We'll print it out again. And what you'll be able to see is that we didn't have to change anything in memory, but we just represented the tensor differently based off its dimensions. So here we have our 2x3, and here we have our 3x2. Okay, so now let's tackle matrix multiplication, which again is the whole point of this project, right? So the fast overview of matrix multiplication is for some matrix A and another matrix B. Their product is computed by taking the dot product between the ith row of matrix A and the jth column of matrix B. And the result of that dot product is the ith jth element of matrix C. So you get something that looks like this. That gives you the first element of the first row, and so on and so forth down the list. So matrix multiplication is really computationally expensive because for each of our n rows and for each of our n columns, we actually have to do 2n ops, because your dot product, recall, is a product between each of the elements in the rows and columns, and then you have to sum them. If you initialize your element at 0, that comes out to exactly 2n operations. So your worst case runtime complexity, which you get, by the way, when you're multiplying two square matrices together, is n cubed, which is not very good at all. So here's what our algorithm would look like to do matrix multiplication. If we represent our tensor as kind of a vector of vectors, right, or that row-wise implementation that we discussed first. So you can see here where the n cubed runtime complexity comes from. We have 3 for loops, and then on the inner loop we have a sum as well as a product, and so that's how we get to 2n ops. So to show how matrix multiplication is going to work for our tensors when we're storing elements in contiguous memory, let's just use this following example here. So in order to get the first element of our output matrix, we have to take the dot product between the first row of matrix A and the first column of matrix B. And recall that we know exactly how to get the first column of matrix B by starting at the first element and then taking a stride equal to the number of columns in B. We do this basically twice, or one less than the number of rows that we have. That gets us the first element of our matrix C. In order to get the second element of our matrix C, we're going to take the first row of A and the second column of B. We apply the same striding procedure, except now we have an offset of 1 from the start of our vector. So now we've iterated through all the columns of B for our first row of matrix A. So now we need to actually apply a stride to matrix A to get us to the second row. And that stride, again, is just equal to the number of columns in the matrix. So in this case, A was a 2x3. So now our stride is length 3. And we can apply the same procedure to finish out our product, our matrix C. So here is what the final algorithm looks like to do this. You can pause it here and maybe work through a simple example. This formula is not obvious at all. I had to spend a lot of time working it out myself. I could have Googled it, but that's kind of lame. You'll notice that, again, this is n cubed, right? So we haven't changed the runtime complexity of matrix multiplication, but because we have fewer accesses to different arrays across the heap, this is actually going to reduce the overall runtime of our program pretty substantially. So there's actually one more trick that we can apply here to speed up our algorithm even more, just by taking advantage of the way that we organize things in memory. So the general rule of thumb is it's very fast to access adjacent elements in memory. So to get from the first element of the second row of A to the second to the third, that's very fast. But when you're making big jumps, or I guess strides, right, across vectors or chunks of memory, that can be very slow because of something called caching. I'm not going to discuss caches, in a lot of depth here, but the general gist of it is the larger of a stride that you're going to take in memory, the slower it's going to be to access the data. So what we can do is we can reduce the size of strides that we have to take by taking the transpose of a matrix. So let's just recall for a second that the transpose of a matrix, basically you take the rows of the matrix and you turn it into columns. So for our matrix B, which is a 3 by 2, we're going to convert that into a 2 by 3 in this way. Now the tricky thing about taking transposes is there's really no efficient way to do it when you store your data in contiguous memory like this. You basically have to just iterate through each element and place it inside of a new vector. So this isn't a contiguous operation in the same way that resizing was or reshaping was. The good news is, though, that all things considered, this is pretty fast. You run this in linear time because you only need to access each element of your original vector once. So that's nice. So now let's take a look at what this actually gives us when we go to take the product of two matrices. So because the columns of B are the same as the rows of B transpose, now what we have is the columns of B are adjacent in memory. So we no longer have to take strides between elements and columns. What that means is now accessing this data is significantly faster. We still have to take strides whenever we switch between the rows of A or the columns of B or the columns of B, the rows of A. But this is one stride that has to occur rather than the number of strides equal to the number of rows in your matrix. So there's less jumping around in memory that's happening here. And so by performing an operation that's linear time prior to our operation that's basically cubic time, right, we can actually speed up the amount of time it takes us to perform the cubic operation. So here's kind of the money slide in this whole video. Basically, as a runtime benchmark, what I did was I did matrix multiplication between two random matrices that are 4096 by 4096. And the machine that I'm using is a Mac M1 Pro. So the naive implementation of matrix multiplication, where we implement tensors as vectors of vectors and we jump all around the heap, in order to perform this matrix multiplication, it takes about 600 seconds, or around 10 minutes. If we then switch our tensor representation to store all of these elements in contiguous memory, we cut down the amount of time here from 600 seconds to 250 seconds. If we then take the transpose of our second matrix prior to doing the multiplication, we then cut down our runtime to 60 seconds. So we end up at 1/10 the runtime of kind of the simple straightforwards implementation, despite the fact that we have yet to do any parallelizing or multi-threading. So here's our implementation of the transpose function for a given tensor. You can see we're iterating through each element of our original tensor, and we're pushing that in the correct order into a new vector, which then we use to create a new tensor, which is the transpose, and we just flip the order of the dimensions here. This does assume that it's 2D rather than an n-dimensional vector. We may end up fixing that in the future, we may not, it just depends on scope. So now when we check out our implementation for the multiplication operation, we checked dimensional compatibility. We implemented that in the last video. But now, right, we're taking our transpose to the right-hand side before then we go through our loop. And in the innermost loop here, you can see this is now what the indexing looks like for each row, for each column, and so on. You can pause here and try and work through an example yourself. Keep in mind, right, we are taking the transpose, so now things are aligned a little bit more in memory. It's certainly not easy, but I think it's a worthwhile exercise. So now that this little refactor of this library is done, the next thing that we're now going to move on is doing gradient descent with linear regression, and then we'll move on to actually training a neural network on MNIST with this library. So just a small channel update. I created a GitHub repo where we can host the source code for all of the projects that we'll work on in this channel. This particular tensor library I'm calling TensoRS, which, you know, RS, Rust, tensors, you get it. So that repo is up. Also, I put the repo up for the prompt package that we created in the video prior to this one. So if you want to go in and check out that source code, the implementation in here is slightly different. This is my personal implementation, but it's a little bit cleaner. And so I figured, you know, that would probably be the thing to share if people are interested. So GitHub's up now. I'll put the link in the description and I'll stick it in my channel someplace. And yeah, go check it out. Thanks. See ya.